Hello, I hope we've all had a great Hopper Day 2, and we've had some really great networking over the last couple of breaks, and you've all been upstairs to the alley that has all the great companies that are demonstrating today about getting jobs there. My name is Alicia Brown and I'm your chair for this session. I come from CSIRO's Data 61. If you want to find out some of the cool things that we do, please step outside and come and have a look, or come chat to me after the break. Today I'm really excited to introduce two talks, and just before we get started, a couple of housekeeping. I'm sure you've all heard this before, but number one, phones on silent, please. Number two, if you need the emergency exit, it is the door that you came into. And number three, the questions, what we'll be doing is taking them at the end. So we give the speakers maximum time to go through their presentations. At the end for questions, you'll be able to queue up behind this mic just in the middle here and ask your questions. Please do make sure you speak into the microphone because we are recording today. So first up, I want to give a very warm welcome to Dr. Pauline L. Pounds, who is an associate professor at UQ and will be talking us through Gyroscopic Bi-Peds, a new way of walking. Please welcome Dr. L. Pounds.
Thank you. All right, thank you for coming. I'm going to try and keep this animated and a little bit lighthearted. There's a bit of math, and I'll warn you before that happens, but if you experience any distress from the math, counseling will be available up over the yeah, okay. Excellent. So I want to talk to you about gyroscopic bipeds. I want to ask a couple of questions. So what if we reimagined how we could build walking machines, how we build robots that can balance and move their feet? What can tightrope walkers and drones tell us about doing an activity that involves balance? And can we build a cheaper dynamically balancing stable bipedal robot? So a little bit about me. I knew I wanted to be an engineer since I was very, very young. I'm crazy passionate about building these sorts of things. And rather than tell you, my citations and things, I just want to show you all the lovely, crazy things that I've built over time, whether it's helicopters picking up boxes and transporting them. We were the first to do aerial manipulation back in 2010. And so Google delivery drones and Amazon delivery drones sort of trace their lineage back to us, or crazy vertical helicopters that fly indoors, and everything in between. But today I'm not talking about drones, even though that's what my background is. I want to talk to you about bipeds. What's a biped? Well, we're each a biped. We have two legs and we walk around. Okay. Now, if you're building a robot to do that, that's actually a really interesting thing to do, because you can go places where wheeled robots can't get to, and quite oftentimes places that flying robots can't get to. And we can build them more compact than quadrupeds, like Boston Dynamics' Big Dog, or even like hexapeds, like the ones that's on display outside, which totally cool, check it out. But compared to quadrupeds, hexapeds, or even flying drones, they're much more challenging to build. They're unstable locomotion, which is to say, if you don't keep actively balancing, you fall over, okay? They're very demanding in that way. You have to have good sensing, you have to have good actuation. And as a consequence, to someone like me, who's an academic, who's really interested in pushing the envelope, they're really challenging and interesting to study. So it's a popular research topic internationally. A lot of people overseas have been working on this, but Australia doesn't really have bipeds per se. And I'm hoping to change that because I think they're really cool. I've been into cool, crazy science fiction robot things since like forever. And my dream is to eventually go from building a tiny robot to building something a little bit bigger, so I can crush my enemies. I mean, yeah. So the immediate question you get is, hasn't Boston Dynamics kind of done it? And there's these beautiful, quite famous YouTube videos of robots that are really good at balancing, even when being assaulted by, well, boots and hockey sticks. Well, that's great. There is, however, a bit of a challenge with it. Though you might think Boston Dynamics has it in the box, and I do agree, it turns out that box is actually really expensive. I'm not sure if you're aware of just how much a Boston Dynamics robot costs. I haven't been able to get figures for Atlas, but even the small Spot Mini robots, the cute little yellow dancing dogs they've been building, are estimated to start at about $100,000. And that's a lot of money for something that, honestly does something that biological dogs already do, and that humans kind of think, oh, well, can I do that? Problem is, there's all sorts of applications where we don't want humans. We have applications where we would like to be able to send robots, whether they be dangerous, dull or dirty, where we would enjoy having the capabilities of bipedal robots, but we don't want to spend the big ticket money on making that happen. Whether it's things like courier delivery for last mile logistics, whether it's something like compound security, like shopping mall parking lots, office compounds, factory floors, where we would like to have a robot just walking in circles, up and down stairs, over curbs, around obstacles, where we can't get a drone to do it because they don't have endurance, we can't get a wheeled robot to do it because of obstacles. That would be great. And even things like, say, I don't know, tour guides. It would be really cool if we could have robots that are nimble enough to be within human spaces designed around humans. We have 2 feet, maybe the robot should have 2 feet. So what do we need? We need a compact platform. So something that isn't widely spaced like a hexaped, something that has rapid dynamics so it can change its direction quickly, it can maneuver and respond to impacts and disturbances, something that can handle stairs, ramps, sort of rough ground, but not horribly broken ground like you would expect in, like, DARPA's military robotics. And we don't want to rely on waggling arms, because waggling arms take up a lot of space and that makes them less compact. It's an artist's impression of what something like this might look like, kind of showing my history of someone who likes to build cool robot things. But really, what we need to compete against in this space is a company called Knightscope. And I don't know if you're familiar with Knightscope, but you may have seen the article which went viral a little while ago, which breathlessly reported how one of their security robots for patrolling a shopping mall wound up getting itself confused and didn't see the entrance down a stairway to a fountain. And it looks a little bit like a Dalek, and it moves a little bit like a Dalek, and promptly went for a swim in the pool. And if you search for Knightscope on Google, these were the 4th and 5th pictures that come up on Google image search. We really just have to handle terrain better than they do. Okay, so let's build legged things. That sounds really exciting. How hard can it really be? Okay, I've used a popular meme here, and I'll tell you why. Not because we can't do math, though the math is difficult with friction and stiction and surface elasticity and limb kinematics and dynamics and servo nonlinear and force saturation. There's a lot to take into account. The problem's not that it's challenging, the problem's that it's expensive to solve those challenges. The thinking meme here is because a lot of people rapidly go out and start doing a whole bunch of number crunching when really we could just think about the problem a bit harder. Why do all of the hard analytics when we can think about the problem and solve it in a different way? So if only we could solve this dynamic stability and locomotion problem as 2 decoupled orientation and locomotion tasks. Big think. All right. My background is in drones, and so my stupid approach here is to treat it like a helicopter. We know drones. What if we build a biped like a helicopter? A helicopter has a couple of key features. It has some dynamics in of itself. It has forces and torques being generated by its rotor, and then it has disturbances coming from the atmosphere around it. All right then. All right. What if we do that with a biped? We know that we've got disturbances coming up through its feet. What if we had some sort of force-torque generator somehow? Excellent question. Where are we magically going to get these forces and torques out of nowhere from? Actually, there is a way. And if you're a tightrope walker, then you would know that you have to balance your center of mass over your contact on the ground, or in this case, a slack rope. And part of the way you do that is by moving your torso in order to generate reaction torques that move your center of mass back and forth over the wire. The reason why tightrope walkers carry a balance stick is because rather than having just their arms to move, they can move the entire stick. And that has a lot more angular momentum that you can transfer to it in order to get bigger changes for smaller movements. That's great, but we don't really want to use big sticks. Here's an alternative.
The first maneuver raises a cubit from one of its faces so that it balances along one of its edges. And the second raises it from its edge to one of its corners.
So here they're using reaction wheels, which is basically what that balance stick is, but with continuous rotation. And these have a long history for use in robotics and things like satellite orientation control. But I'm going to suggest not reaction wheels. And my reason for that is because reaction wheels have this interesting property where when they're stationary, you can apply a lot of torque to them. But when they get up to their maximum speed, your ability to put torque into them and therefore get a reaction torque to push you back the other way degenerates to 0. And if you want to get better momentum change, you've either got to have bigger wheels or higher speeds, which means higher voltages. And large wheels, large voltages is actually really hard to work with. We want to do something which doesn't rely on that so much. What can we do about that? Well, my solution, as you've probably sussed from the name of this talk, is to use a control moment gyroscope. In this case, we use a high-speed disk, such as a wheel or a gyroscope or some other reaction mass, and we spin it around, but rather than simply trying to make angular change in the plane of the axis, we then tilt it sideways to get a reaction torque. And so in addition to increasing the mass of your system to get more reaction torque, you just make it spin faster. The faster it spins, the more angular momentum it has, and therefore the more cross-axis angular momentum you can apply. Okay, that sounds really complex and highfalutin. Tell you what, let's make it simple. I brought a wheel. Who here remembers high school physics class? Yeah? Okay, let's see how this goes. If I spin that up and I tilt it, I'm trying to tilt it level, and it won't let me. It always kicks to the side like that. In fact, the faster I spin it, the stronger that gets, to the point that I can actually suspend it out lightly on my hand, and you see it starts to rotate in a circle. That rotation sideways is it counteracting the gravity vector being applied to it. So we can get really strong reaction torques out of a wheel just by spinning it fast. And we don't have to move it very far. We don't have to make it very complicated. And if we want to get more out of it, we just spin it faster. Okay, so here's a little bit of math. This isn't too scary, okay? Bear with me, it's all right. So I really want you to just take away 3 values here. One is the velocity of our spinning rotor. One is the velocity being applied to the gyroscope to tilt it, and one is the rotational inertia of the rotor itself. And what we want is we want to keep our angular velocity of the rotor high. We want to keep the rotational mass high without having to have very heavy rotors. And we want to keep the cross-axis rotation slow so we don't have to have very expensive servos. And if we sit down and think about it, we can come up with a solution for this that makes it possible to compensate for the forces acting on a gyroscope biped. So let's do some design. Suppose we want to build, say, a 1.5 kilo platform. That's not real big. It's quite tractable. Let's say we're going to have 2 actuated degrees of freedom for each leg for locomotion, 1 in the foot, so that's 6 plus 2 for the control moment gyro. That gives us 8 actuators. And if we have small servos that are 50 to 70 grams, we wind up spending about 500 to 600 grams in actuation. Spend 40% of that estimated mass on just the chassis, so the physical frame of the robot. That brings us up to about 1.2 kilos, and that gives us about 150 grams for batteries and control, and 150 grams for our spinning object, or about 10%. I have no idea if that's enough, but it seems reasonable. Okay. Let's actually put that into our engineering software a little bit and see if we can come up with real numbers. So when we actually try to build the thing, we wound up requiring about 1.3 kilos for the whole robot. It ended up being about 24 centimeters tall, 150 millimeters to the hip, and the ankles are about a little under 2 inches apart. And we ended up building a 156-gram gyroscope. I'm really glad we kept it so close to what we designed around. It's got a fairly nice angular velocity because we've designed it well, and our gyroscope control motors give us plus or minus 180 degrees, so almost a full 360 of rotation. And we can spin up to 23,000 RPM, but we would want it to spin at about 13,000 RPM. That's actually a lot, even if you don't think about it much. That's much, much faster than a drone rotor for comparison. Do some numbers, and we wind up requiring between 13 kilogram centimeters for the knees in terms of torque, and 6.5 kilogram centimeters of torque just to stabilize on the gyroscope module. We went out and we found some beautiful hobby servos that give that plus a little bit more, so we think that's pretty cool, and their speed's pretty high too. Okay, we would love to build something much bigger than 1.5, but we don't have the funding, but this seems like a pretty good place to start. Now at this point you're probably saying, yeah, look, that's cool and everything, how's it all fit together? Well, we got kind of excited and said, let's go out and put it together. And then it occurred to us we were building something with high-speed spinning things. And I've had experience building high-speed spinning things, and one of the things I've learned is not to take them for granted. So we did some safety analysis. And it turns out that when you have a flywheel of the size that we've got, which is about that big, it's about $1,000 worth of machining there in units of one. It'll get cheaper in mass production quantities. If you spin him at 23,000 RPM, he has the same energy as a 9mm bullet, which is sobering when you think that you're going to be working in close proximity with that. If you actually operate it at the speed of what our design says we should require for balance, it gets a little bit more sane. It's only about 131 joules, which coincidentally is the speed of the world's fastest cricket ball pitcher, I believe, throwing a cricket ball weighing exactly the same as this. So if it's as bad as if I'd threw this at you very, very fast, which is a little bit less intimidating than being shot. That said, if you're going to build something that's going to be the energy of a bullet, you want to build your system to be bulletproof. So the very first enclosure we built is made from very similar material to that that's in the hull of the Bradley Armored Fighting Vehicle, 6061 aluminium. The Bradley actually uses 5083 aluminium, slightly different because this has silicon in it, which makes it less weldable, but never mind. Okay. So as you can see, it's 1/4 inch thick. That will stop any fragments we're likely to have. And if anyone comes to shoot me, I'll just put that in the way. All right. We then decided, that's cool, but we're not going to be confident that it's not going to kill us until we torture test it a bit. So we built a platform whose sole purpose is to test it and test it and test it and test it until it breaks. And what we found is that when we do maximum speed motions of our gyroscope system running at not just operating speed, but full speed, we couldn't break it. We could not actually get our gyroscope to fail under load. In fact, what we found is that our testing gimbal system actually broke because it was 3D printed after about 100 oscillations. And at that point, we sort of said, yeah, we're fairly confident if it can survive that much, it's going to be fine for our testing. Spoiler, we didn't die, so that's encouraging. Okay, so here's one we built. We finally got around to actually putting it together, and I have him there on the front. I'll give you a little demo at the end. The great thing about this guy is compared to $100,000, though he's only pint size, he is also only 4,000 something Australian dollars, which for experimental robotic systems is actually an enormous discount. So we're succeeding in our effort to make things cheap. If you have a look at what's under the hood, there's a whole bunch of axes and pivots for the gyroscope module. We have pin joints in the hips, pin joints in the knees, and we have totally free wiggling feet. So our feet are actually, they're so cute, look at that. Wiggle, wiggle, wiggle. All right. And that's so that they act like pin joints when it's trying to stabilize itself. Otherwise, dissymmetries or small offsets in the feet would translate into forces into the body that then have to be corrected for. Inside, you can see there's our gyroscope. This one's got a slightly updated enclosure, which uses a stainless steel as its protection belt in addition to the aluminum housing. So it's still very, very safe, but shaved about 100 grams off the total weight. So how does it walk? Well, we like to joke that it's a case of putting one foot in front of the other, and that's absolutely true. Basically, it goes through a simple fixed gait cycle that's a series of cycloids. I won't subject you to that at the moment. And its alternating foot stance is rather interesting because walking in a straight line, the legs are always aligned with the body. If you want to turn the corner, then during each of the foot stance phases, you give each of those feet servos a slight twist as it's going through its motion, and that causes the next foot to be put slightly to the side. And that allows you to go through a curve. And you can even do that standing on one place by just twisting your legs as you walk around. Very similar to what we do. Okay, quick warning about the math. Math coming up. It's all right, you can look away. I like the math, that's all right. So we have a dynamical model, which is that of an inverted pendulum. So it's a second order system. Do a Laplace transform if you know what that is. If not, don't worry. But the key thing is we have, my laser pointer, there's our dynamics, there's our torque entering the system, and these little guys are our disturbances coming from the foot poses. This guy here is a second order controller. It's just a proportional derivative controller. If you know what PID is, it's PID without the I. All right. We can actually calculate what those little forces acting on it will be simply through the leg kinematics, which is to say, if we know the pose of the leg at every point, we can compensate for the forces that should be acting by simply doing a static force analysis. It's really, really simple, but it allows us to say, hey, I know I'm going to be falling slightly forward. Why don't I apply the equivalent torque back before that happens? And I can compensate for it before it even begins. All right. So there's a couple of catches. As I said before, the problem with reaction wheels is that they saturate. Well, control moment gyros saturate too, and they saturate at that point where your wheel has twisted all the way to 90 degrees, and now there's no way for me to apply torques to that wheel that'll produce a counter torque in the direction I want it to go. What am I going to do there? That's a big problem, isn't it? Well, I have a really simple, stupid solution for you. It's an alternating gate. So if I'm falling over one way all the time, and I'm moving my wheel forward to compensate, then when I'm over this side, I need to be moving my wheel backwards to compensate. And as long as I'm switching legs often enough, my wheel's going to move forward and backwards, but it's never going to go all the way to gimbal lock. So as long as I'm mindful of the maximum air time that my robot's leg can be up for, that's okay. Because we can't do what humans do, where we actually shift our center of weight over our balance, and I could be here all day, I'm not going to subject you to that. The robot actually can't use those sorts of strategies, but it has a second strategy, which is slightly moving its center of mass to compensate, and I'll explain how that works. If we have small bias forces, like say an imbalance in the torso construction, or say a mechanical impingement on the robot, like it's brushing against something, then that's going to be constantly entering the system dynamics. And if we don't compensate for that force, our gyro is just going to go crazy trying to compensate continuously. And at some point, we're going to run out. We need some way of getting away and dealing with those bias forces that doesn't require our servos to saturate our gyro control. What can we do? So two simple solutions. First of all, because we have a center of mass above a pivot, we can lean forward and we can lean back. So we can actually drive our robot that way in order to allow our gyroscope to compensate along its pivoting axis that way, because it's always 90 degrees out because of gyroscopics. As a result, even if we have a little imbalance, as long as we can tilt our body to act as a compensator, that's no problem. In the opposite direction, we have the interesting phenomena where if I'm standing with my two legs together, I can take very large forces pushing against me along that axis. And in fact, for any two stance leg positions, which has to happen every time you go to take your next step, if instantaneously while I'm along that axis, I move my gyroscope parallel to that, then the forces through the reaction with the ground will compensate for that. You'll always be stable moving your gyroscope in line with your stance legs. Easy. All right. So what about the control design? If you take all of those three things, PD control, some feed-forward compensation from knowing your kinematics, and then some relaxation control to compensate for bias accumulation, you get a thing that looks like this. And if you're not a control theoretician, that probably doesn't mean anything to you, but it's relatively straightforward once you get under the hood. If you simulate it, you get something that looks like this. And I really like this because it doesn't go crazy, it doesn't break, it just seems to work. And it works for long strides and short strides just nicely. Okay, enough talking about it. Here's one we built. So here you can see it's got its moving system, it's got its two legs together. We're only worried about one axis at the moment. And our gyroscope is wiggling around trying to keep it balanced over its ankles. There's a weird little glitch there, which actually is a consequence of the way we were interpreting our IMU. And that caused it to instantaneously think it was 45 degrees out of where it was. Once that 45-degree error cleared, it then goes back, rejects that disturbance, and drives it back level again. Because we're scientists, we actually have some data, and here you can see where that glitch enters the system, goes to a transient, and rejects it. We then redid the experiment, and I won't play the video for you for time, where we modified our data bus to get rid of that and give us more resolution on our measurement, and it works just fine without any glitches at all. Okay, so where are we up to? We have longitudinal stability in our biped. We have all of our drivers and controls done. We have a whole bunch of cables that were out of the prototype that you saw in the video that we've removed, so it's all nice and cleaner now. We've rebuilt the system on a new 32-bit processor to get rid of some of those data glitches, and we can run at 400 Hertz internally. We only need about 100 to implement the control loop. We're ready to start testing our lateral stability and moving to walking. So what's next? We want to prove our feed-forward control, implement that with a leg swapping dynamically, add some ground contact sensors, add some servo gating for doing motion control, and I actually have a demo of that, but I might wait until the break because we're a bit short on time, and then add some obstacle detection and start building up the ability to walk and then avoid obstacles and be more mobile in the environment. And hopefully one day we'll build a less tiny giant robot because, you know, the sky's the limit, especially when it comes to crushing my enemies. All right, so this has been the work of myself, my tech officer, Will Deere, and a whole host of students. And if you're interested in robotics, that host of students could include you as well. So if you find it interesting, please let me know. We have about 2 minutes left for questions. I'm sorry for running slightly long. Otherwise, if you have no questions, I can do a quick demo. Demo? Okay. All right. Unfortunately, I don't have it in a state where it can walk. I really, really wanted to have it for you, but it didn't quite happen. But I can turn it on, and you can see it jiggle and wriggle and generally scare the crap out of me. So it's worth mentioning that as much as we worried about the safety of the gyroscope, the servos themselves are incredibly strong. And if you stuck your finger in while it was maneuvering, it would just take your finger off. So if that happens, please do get some help. I mean, for me, you might also need emotional help. It's possible too. All right. Let's see how this goes. It likes a little bit of time to start up. There we go. So it pulls its legs up because we like to start it with it in the sitting position, but that's not good if you want people to actually see what's going on. So the first thing we do is we turn on the gyroscope. I've actually disabled the gyroscope because as much as I like you, I don't want to subject you to, a potential rifle bullet in the room. I'd need ethical clearance or something to use you as my guinea pigs. Instead, it's just got a counter that takes the time that it requires for the gyroscope to speed up. So please hold. Your call's very important to us while it just goes through its internal speed up system. There we go. So that's the onboard controller turned on. And you can see that as I move the robot, it's actually quite aggressive because it's actually an unstable controller that's compensating for the instability of the system itself. And if I leave it on its own, it will actually start to go unstable because it doesn't like being suspended like that. But we'll let it go through its trajectory system. So where we were supposed to be was this should have been balancing with its gyroscope, but there's still a control measurement error in there that's keeping us down. But we're very, very close. Here you can see it's walking backwards, then it will stop, walk forward. And it's probably difficult to see, but there's a section where it actually wiggles its feet as well, which is always cute. So I'm out of time. I'd like to thank you very much for your attention. And if you want to have a look at them after the talks, please come up during the break and I'll show you the toys in person. It's all about the toys.
Please give Dr. Pounds a warm welcome. Thank you. Good afternoon, everybody, and welcome back to this session. We're going to kick straight off into it, so if I could have your attention, please. It gives me my great pleasure to introduce our next speaker on this afternoon's bill, software engineer Sally McFargan from Pegasus. Some of you may have seen Sally's work in the workshop yesterday and also heard some of our other Pegasus speakers yesterday. Today, we're here to hear the anatomy of a blockchain client. If you can please give Sally a warm welcome.
Okay, welcome. So I'm going to talk to you about the anatomy of a blockchain client. So blockchain it's a new way to store and verify immutable distributed information that is readable by anyone who can access the blockchain. So what's that all about? What is a blockchain client and how does it work? Before I get into that, just quickly about me. I'm a software developer. I have been for about 20 years. I've worked in various industries, and in the last 18 months, I'm now a blockchain protocol engineer. So I work for Pegasus, which is part of Consensus, and we are building Pantheon, which is an open source Ethereum client. Okay, so really quickly, what is blockchain? You can think of it as a chain of blocks. So every block is connected to the block before, hence a chain. It's immutable, so once something is written to the blockchain, it cannot be changed. The only thing we can do with a blockchain is append to the end of the blockchain. It is public by default, so anyone with a blockchain client can see everything that's on the blockchain. My colleague Sandra Johnson did a talk yesterday about trust in a trustless environment, so you don't need to trust the other people who are in your blockchain network to operate in the blockchain network, so we can think of it as a trustless environment. So our Pantheon client is an Ethereum client, so just quickly, what is Ethereum? So it's a blockchain platform, it's immutable, public, as a good blockchain is. The public Ethereum blockchain we call mainnet. We also have a notion of private Ethereum networks, so you can run up an Ethereum network that's not connected to mainnet, and that's what we call a private network. So really quickly, what is Pantheon? It's mainnet compatible. We're also building enterprise features into it. It's written in Java and it's open source. You can go to our GitHub repo, download the code and start playing with it if you all want to do so. We are targeting EEA compliance, which is basically standardization for the enterprise features. It's a flexible modular code base. We support multiple consensus algorithms, which I'll talk about a bit later. And we've put a fair bit of work in to making sure that it is well tested. Okay, here's an anatomy diagram. So we know what the blockchain is at a high level. So when we think about a blockchain client, the only thing we can do with our blockchain is add blocks to it. So that's what our blockchain client does. It makes blocks in the case of a miner, and it adds blocks to the blockchain. In slightly more detail, not all blockchain clients will make new blocks, only miners do that. I'll talk about mining a bit later, but the miner is that bit there. So not all clients will make blocks, but all clients will be listening out for new blocks and adding those new blocks to their local copy of the blockchain. So we use Dev P2P here to talk to our peers, to talk to other blockchain clients, to listen out for new blocks, and if we are making new blocks, we broadcast those to our peers using Dev P2P. So we've got mining and block propagation. The other important piece is consensus. So when a new block is created, the consensus mechanism is the way of all of the players in the network agreeing that this block is the one that gets appended to the blockchain. So we've got mining, consensus, and block propagation. Okay, so I'm going to talk about some of these pieces. So the core over there is kind of the engine room where the high-level concepts of transactions and blocks are taken care of. The next bit is chain processing, so that's importing new blocks and adding them to the blockchain. Peer-to-peer, so that's how we talk to our peers, the kind of network and protocol, which I'm not going to go into too much detail today. And the last bit over here is the state, so that's the actual storage. And the bit over the top is JSON RPC, so that's, you can think of that as the user interface for Ethereum. So that's where apps, dApps, MetaMask, all those applications that actually run on Ethereum will talk to the blockchain client via JSON RPC. And JSON RPC can talk to all these different pieces of the blockchain client. Okay, let's move on. So we'll start with state. So state, there's two kind of main pieces here to store. So the blockchain itself is the history. So we talked about it being immutable. So once something is written to the blockchain, it's there in the history. So the blockchain piece is kind of keeping track of all of that. So we've got block headers, block bodies, receipts for transactions. We have this notion of block difficulty. So that can change from block to block. So that's stored in the block itself. The canonical chain, that kind of notion is the agreed version of the blockchain. So that's the one that all the blockchain clients agree to be the latest and best actual chain. And again, the only mutation that you can do to the blockchain is appending a block. So the blockchain is the history. The world state then is the current state of things. So that's the here and now. So we've got things in there about accounts like the account nonce, the account balance, and the actual code that can be at an account address. So if I want to know, say, the balance of an account, how much ether does this actual account have, I could go back to the history and replay all of the transactions to derive that account balance. But it's much easier if I can just go to the world state and query that kind of like a SQL query. Just give me the account balance of this account. So the blockchain is the history, the world state. It's built up over time, but it's kind of a picture of the state of things right now. So all of that is backed by key value storage. For Pantheon, we use RocksDB, and basically the key is the hash of things and the value is the actual data. Okay, so chain processing, we said this was adding new blocks, so updating our chain. Okay, so when we get a new block, so up here tells us we've got this new block. So the first thing we do is ask, is this block valid? Can I add it to my blockchain? So we have a way of validating the actual block. So the synchronizer actually gets the block headers asynchronously, so we can kind of validate the headers in advance of getting the actual block body. Interestingly, the block header validation changes with different consensus algorithms, but I won't go into too much detail of that just here. So we validate the block, we validate the header, we validate the body, and then we can actually validate the actual transactions that are in that block. So once we've decided that yes, this block is valid, the block importer is the piece that actually adds that block to the chain. So it coordinates that whole process of validating, processing, and importing the block. So the block processor, it uses the transaction processor, which is down below. Sorry, wrong button. So the block processor uses the transaction processor, and it also pays the block reward. So that reward goes to the miner, which was the client that actually produced this new block. So they get a little bit of a reward for doing the work of producing that block. So then we can validate all the transactions that are in that block. So they get processed one by one. I'll briefly mention the EVM, which is the Ethereum virtual machine, which executes the actual transaction code. And I will say no more about that. The transaction receipt, so that's kind of the summary of when and whether that transaction actually was executed. Some other bits and pieces here. So we talked about the block reward, the gas calculator. So this is kind of a way in Ethereum of making sure that we don't spend too much of our resources on processing a particular transaction. So someone can't sort of submit a transaction that's got an infinite loop or something like that. So we work out how much work will this transaction take to execute and make sure that the person has submitted enough gas to actually execute that transaction. So I mentioned the difficulty, so that can change from block to block. So in Ethereum, we want blocks to be produced about every 15 seconds. So if things are happening too fast or too slow, the difficulty is basically a way of adjusting that, those calculations so that we can get blocks at that regular interval. The block hash function, so that's how to calculate the block hash from a header, and again, that differs with different consensus mechanisms. Okay, so let's just quickly talk about consensus mechanisms. So proof of work, this is the one that's used in Ethereum mainnet and also Bitcoin. So you can think of it as a cryptographic puzzle that's hard to solve, but the solution is easy to verify. So it's deliberately inefficient. So essentially all the miners are competing to solve this puzzle so that they can have the honour of producing the next block. And this works in trustless environments, so such as mainnet. So you don't know who all the other people are. We don't know who we can trust and who we can't trust. So that's where we use proof of work. Proof of stake is a bit different. So in proof of work, if you do the wrong thing, you will lose the computation, you know, the resources that you've spent on doing that computation. In proof of stake, if you do the wrong thing, you actually lose your stake, actual ether, cryptocurrency. So essentially in proof of stake, there will be different parties who've staked an amount of ether, and they can essentially take turns in producing the next block. So it encourages trustworthy action, and that's what Ethereum is moving to in Ethereum 2.0. Proof of authority is similar, except instead of staking ether, you stake your identity, essentially. So we use that in networks where we know who the people are in our network. So we have specific nodes as authorised miners, and essentially, again, they take turns, and we can vote people in and out of that pool of miners, and it's a lot more efficient than proof of work. Okay, so this is, if we look at the core now, this is the Synchronizer. So the Synchronizer's job is basically to catch us up from wherever we are, which could be the Genesis block. That's what we call block 0. So we could start at block 0 and we need to catch up to the chain. So that's the job of the Synchronizer, to catch us up and then to keep us in sync. So the Synchronizer has two main parts. The first one is the downloader. So the downloader's job is to do that catching up piece. So essentially, we're down here somewhere. We want to catch up here. So we find a best peer to sync from. So whoever has the best, latest block, essentially. And we ask that best peer for, we find our common ancestor. And then we also ask it for some checkpoint headers. So we're not going to ask this one peer for all of the blocks, because that might be 7 million or some really big number of blocks, but we ask them for these checkpoint headers, and then we fan out requests to a number of different peers for all the blocks that are in between. And when we get to a checkpoint header, we essentially use that to validate that those peers are giving us good information and it all matches up. So that saves us from syncing 7 million blocks and then realising that something's wrong. We can check at those different intervals, and then if something's bad or broken, we can throw it away and start again, but not from scratch. So the downloader catches us up, the block propagation manager keeps us in sync. So we're listening out for with our peers for notifications of new blocks. And when we get a notification of a new block, we check firstly, do we already have that block? If we do, that's great. We don't have to do anything with this one. If not, am I in a position that I can add this new block to my blockchain, i.e. do I have this block's parent? If I do, I add it on. If I don't, then I send out requests to my peers for the blocks that are in between. The block propagation manager also keeps a picture of our peers. So when we get a new block from a peer, we basically update our picture of that peer to say, well, they're up to this block number. The transaction pool. So we talked about receiving blocks. So here we're receiving transactions. So we can receive transactions either from our network, so a peer, via dev P2P, or from our local users via JSON RPC. Either way, the transaction goes into our transaction pool, and we also send those transactions to our other peers via dev P2P. And the miner will pull transactions from that transaction pool to construct a new block. So the miner, I just give it a box because it doesn't do anything else. It just pulls transactions out of that transaction pool, solves the puzzle, makes a new block. And that is all the detail that I had planned to go into here. So that's back to our architecture diagram. I also said that I was going to go into some use cases, which I didn't do a slide for, but some use cases for blockchain, and Samantha Reynolds from Microsoft gave a really great talk earlier today about lots of different use cases. But some of them are, so supply chain. So because blockchain is immutable, distributed, everyone's got the same information, it can't be changed. So for supply chain use cases, that means we can verify, using the blockchain, we can verify sort of the record of a particular artifact in a supply chain. So things like verifying that a diamond came from where you said it came from. It's also used for wine, it's used for designer handbags, it's used for, you can integrate it with IoT devices to make sure that vaccines through the supply chain have not gone outside of this temperature range. Milk, same kind of deal. There's lots of financial use cases, so peer-to-peer, micropayments, disintermediation, getting rid of the middleman, getting rid of that point of centralisation. Audit, traceability, verification of identity. There's a whole stack of use cases out there. But yeah, that's all I had. So I guess we've got plenty of time for questions.
Do we have any questions from the room? Would you like to come up to the microphone after?
Probably loud enough.
No, because we're recording. Thank you so much.
Hi, I'm Chris from CSRO, Digital Careers. I was just wondering, is there a particular reason why you use the RocksDB? Could you use any other DB than that one? So that's the first question. And the second question is, in the miner, like, what about the whole process makes it applicable for all other uses other than just Bitcoin mining? So that part wasn't clear for me. So
Okay, so
yeah.
I'll answer the database question. So yes, you could use a different database. It doesn't, for this purpose, it just needs to be a key value storage. It doesn't need to be a relational database. So RocksDB fills that for us, but I'm sure there's plenty of others. The mining question, so the mining puzzle, it just has to be something that is hard to compute but easy to verify. So Bitcoin uses something different to Ethereum. There's plenty of other cryptocurrencies that use different mechanisms there, but that's essentially the core of it. Any other questions?
Yeah, so this is probably really dumb, and I'm really new
There's
to
no
all
stupid questions.
but I'm really new to all of this. But the code is open source, so is it something that someone evil out there could actually rewrite? And because you said there's validators, and that they could use it for their own purpose and have validated blocks that actually aren't really valid.
Yeah. Yeah, that is absolutely true. But the power in the blockchain network is it's one person can't just say that this is the case. In the case of validators, you'd have a pool of validators. In the case of a network, you have to take over 51% of the operators in the network to be able to achieve consensus.
And you couldn't have a pool of corrupt people that all...
Yeah, sure. But if you've got that many people, the cost involved in taking over, you may as well just do the right thing and be a miner.
Okay. And the other question I had is, you mentioned complexity. The miners, if you mine something that's got more complexity, do you get paid more money?
The algorithm is set up so the reward that you get for mining a new block is set. So the adjustment of the difficulty is just to speed things up or slow things down. It doesn't change the amount of reward that you get.
How often does the synchronizer sync?
It sort of does it on demand. So when I start up a new Pantheon node, it will search for peers and start synchronizing straight away. But once I'm in sync, it can sort of slow down that computation because then I'm just listening for new blocks rather than trying to catch up.
So is it constantly listening?
Yep.
Any other questions? Yep, down here. Get my steps up, thank you.
Has there been any analysis on whether or not using a blockchain rather than a traditional database storage, the impact of, I guess, does it require a lot more energy?
Yeah, I think there's plenty of analysis out there on that, and that's one of the reasons. That's one of the reasons why Ethereum's moving away from proof of work in Ethereum 2.0 because it does basically it's deliberately inefficient, so it does use a fair bit of computing resources.
Hi, yes. I wanted to ask, because there's this concept that every node has access to the entire chain. At what stage does, but just for storage reasons, at what stage do you start breaking that up and they no longer have full view of the chain? And how does it deal with the risk of if there's only a certain number of machines which contain the state of, I don't know, a particular number of transactions? How do you prevent someone, taking those systems down, but having stake enough to actually replace the actual correct data with their own?
Okay, so in Ethereum we have a concept of we have full nodes and archive nodes, and archive nodes have the full story. I guess if there's only a handful of archive nodes, you could mount some sort of attack, but again, you'd have to have a fair bit of computing resources to do that, and then you may as well just be a miner.
I was just wondering, in the proof of work model, is it possible to have a branch? Can multiple nodes solve the problem at the same, or miners, sorry, solve the same problem around the same time, and then distribute that to their neighbours? And
yeah, so we call that a fork in Ethereum. So you can have different chains of the same length, and they can sort of have the same value, but at some point one of them will win, and then we have what's called a chain reorg, and things do tend to get moved around at that point.
what is it that they win, sorry?
So it's to do with the difficulty and the length of the chain, and there's an algorithm to say kind of the weight of the chain based on those things. So if you've got two pieces of the chain that are the same weight, they'll have the same value, but so they're both adding new blocks, and at some point one of them will be worth more than the other one, and that will be the canonical chain.
I'm just wondering, if you have these questions that take a lot of computing power, where is the line that you draw and you say, all of us competing to solve this is a waste of energy? And, you know, I don't understand it completely, but where is that waste in energy? Do you think that I could say, okay, I'm going to do this one, you can grab the next one, or, you know, is there a possibility for collaboration, or are we just going to waste that energy and say that's part of it?
Yeah, so proof of work is deliberately inefficient, and that proof of work is used in trustless environments where we can't trust the other players in the network, but where we can have that trust, then we can use proof of stake or proof of authority, which are much more efficient.
Can you just explain those for people that don't know?
Yeah. So I've only got about a minute left. So proof of authority, basically you stake your identity, and so proof of authority works in a network where you know who all the other players are. So if I am a validator in that network and I do the wrong thing, well then you know it was me and you would vote me out of the network. So I lose something by doing the wrong thing. Proof of work we use in cases where we don't know who the other people are.
One last question? All right.
So just out of curiosity, with the synchronization that you were speaking about, and you said that when you spin up a new node, it sits there listening for events. I was just curious how often events were missed, and if that ever did happen, was there a way to detect that, or is that just not an issue?
So what the synchronizer is listening for is new blocks. So if I missed a block, then if I missed block 99 and then I get block 100, then I just go out and ask my peers for block 99.
Right, so you can't make accidental, wrong decisions based on having misinformation. You would just sort of wait, or?
Yeah, so you just wait until you can kind of fill in those gaps. Yeah.
Such a great lot of questions, and let's all thank Sally for being a good sport and fielding them.